one small problem is that this is not causal. Right? How do I make it causal? Shift it by 1. So instead of 1z, how do I shift it by 1? Multiply it by z inverse. And make it z inverse 1. Okay? So in the order up here. And what is Fp of z? Having P of z. For this example, z to the negative 1. What is L hat? For this example, I have a z inverse here, z inverse there. What is that? 2, 1. Right? Because this and this is identity. You have z inverse, z inverse. This and this identity you can put them out. Right? So z inverse 1. So L hat 1, L is 3, and you have rank 4 system. Okay? So in general, you can build a orthogonal filter very, very easily. All you have to do is cascade a block with delays like this. 1 z inverse. Orthogonal matrix. 1 z inverse. And so on and so forth. Okay? So let me summarize it in the other board. Okay? I want to summarize orthogonal filter pattern. So in general, we have the inverse, 2, we have orthogonal matrix U0, the inverse, U1, so on, right? The inverse, U of L hat. It can be anything, right? Depending on how many blocks you have. Okay? So you stop at 1, you have rank 4, rank 6, rank 8, so on and so forth. Reconstruction is very, very simple, right? Reconstruction would be we have U transpose L hat, and you lay up here, so on. We have U0 transpose by 2. How many delay do I have here? L hat 1. Minus 1? No, L hat, right? If I stop right here, I have 1 delay. So L hat. And this product will give you zeta minus L hat. Okay? So U, UK, cosine theta k, sine theta k, minus sine theta k, cosine theta k. That's how you build a general orthogonal filter pattern. Just by cascading orthogonal matrix. Right, from here to there. It's orthogonal, it's guaranteed orthogonal. Such that you have good filter, right? You want H to have a good low pass filter, and good high pass filters, and so on. Applications say that the way I use this filter is to decompose my signal into low pass range and high pass range. If these filters are not good filters, then I'm not doing a good job. Right? And you can show that if I choose this arbitrarily, the filter will not be very good. So that's a design question of how to choose the filter state such that you have good filters. Okay, that's one good, but it's not the most important one. So that's a good question to have, practically. But in theory, I'm looking for theoretical questions right now. Computation, I know exactly how much computation, because I know how to implement it. I know how many of this guy, I can count the number of multipliers. Okay, so if somebody gives you a structure, right, and say that if I choose this theta k, I'm guaranteed to have a orthogonal filter line. So given UK, given theta k, I get orthogonal filter line, right? Orthogonal filter line is H0, F1, F0, F1, right? And you can prove it from here. As long as theta k, as long as you're using this form, so arbitrary theta k is a case orthogonal, and therefore the system is orthogonal. It's the simple proof. That is a difficult one. Right? What does it say? It says that is this the most general system you can think of? It's not useful to give me a system that does not cover everything. Right? Because if this is not general, I might not be able to design good filters. Right? Because, okay, so you have to provide if and only if, right? You have to show that it's not only give you orthogonal filter line, but it's the most complete structure. So, completeness. Completeness means that it's the most general structure. In other words, if somebody not using this kind of design, right? Maybe using half band design. Okay? Give you a 4 filter that's orthogonal. And you can do that, right? Using half band, you factorize this such that F0 is H0 flipped, and you know H1 F1. Take those filters, it's just orthogonal, and I'm giving that to you. I will say that. Can you find me a unique set of theta k that represent those filters? If the answer is yes, then your structure is complete. And therefore it's a most general structure. If the answer is no, this is not useful. Right? So how do I show completeness? How do I show this? This is easy. How do I show that? You have to come up with a way to synthesize. Meaning that we start with the filter here, we're going backward. Right? So we start with a set of filters, we're going backward. Synthesize this block. Okay? If this length 4, we're going through here, it's length 2.